All right, it says answer the following questions about ascorbic acid. Okay, so we have an acid question here. Student combusts a sample of ascorbic acid to determine its chemical composition. The only products of the reaction are 0.2400 molar CO2 and 2.883 grams of H2O. And it says calculate the moles of H2O produced. So that's a simple calculation we can do. So let's take 2.883 grams of H2O, and we're going to use the molar mass, 18.02, and we're going to go ahead and convert that to moles. So let's plug that into our calculator. So 2.883, divide that by 18.02, and we get 0.159. So we're going to round that actually to 0.1600 moles of H2O. All right, part 2 here says the mole ratio of carbon to oxygen is 1:1 in ascorbic acid. Based on the information in the answer to part A, determine the empirical formula. So we have our information that the moles of carbon to moles of oxygen in ascorbic acid is 1:1. So what that's telling me is that if I have 0.2400 moles of CO2, that means I have 0.2400 moles of carbon, 0.2400 moles of oxygen. And then here, I have my moles of water, but what I need to take into consideration is that there are 2 hydrogens for every 1 H2O. And so this ends up being 0.3200 moles of hydrogen. So if I were to move forward with the empirical formula, I wish I had room. That's the only thing I wish I had more of in these questions is I don't have any room to write, and it's frustrating. I'm going to go ahead and get rid of these little markings here, okay? And I'm going to go ahead and put the 0.3200 moles of hydrogen here. So we have all of our mole values. So remember that when we do empirical formula, we divide by the smallest mole number. So we're going to divide by the 0.24 for each of these. So we end up with carbon 1, oxygen 1, and hydrogen 0.32 divided by 0.24, 1.33. And so because not all of these are equal to 1, we're going to go ahead and need to multiply all of these to get the appropriate empirical formula. 1.33, the least common multiple of that to give a whole number is 3. So we're going to take all these values and multiply them by 3. So what I end up with for my empirical formula is C3H4O3. And I don't think it really matters here exactly what order you put them in. Obviously, if it's an acid, most often the hydrogen comes first, but it just tells me to put it in this order here. So that's exactly what I'm going to do and what I'm going to leave it as. So yeah, that's what we're going to do, and I'm quite content with that. So it says here, ascorbic acid acts as a weak acid, as shown in the following equation, and it says the following titration curve was produced when 10 milliliters sample of ascorbic acid was titrated using 0.055 molar NaOH. And it says here to calculate the molar concentration of the ascorbic acid solution. So this is just going to be find the equivalence point and utilize the M1V1 equals M2V2 in order to be able to solve for this. So the equivalence point's right here at 16 milliliters. So what that tells me is that the concentration of acid, which we'll call M1, we use 10 milliliters of it, so 10.0, equals the concentration of the base, so 0.0550, multiplied by the volume of base that's added, which is 16 milliliters. So if I go through that and algebraically solve for M1, I should get my answer, 0.0550 times 16. And we're going to divide that by 10. So what I end up with is a molar concentration of 0.088 of the ascorbic acid solution. We'll abbreviate that HASC just like it does here. All right, let's see what we got next. So it says next to determine the pKa of ascorbic acid. So in order to solve for the pKa of the ascorbic acid, remember that pH equals pKa at the half equivalence point. The half equivalence point, the equivalence point is at 16. The half equivalence point's at 8. So right here, this is where your pH equals your pKa. And so it looks to be about 4.1 for the pKa value. And then lastly, it says, what is the value of the ratio of base to acid So this is a Henderson-Hasselbalch equation when the pH of the solution is 4.7. If the pH of the solution is 4.7 and the pKa is 4.1, we know that when we add that to the log of the concentration of the base over the acid, we can just algebraically solve for this pretty easily. So subtracting these values, we get 0.6 equals the log of the concentration of base over acid. And so we're going to take 10 to the 0.6 power to get the ratio of base over acid. Simple enough, because 10 to the power of is the inverse function of the log. So 10 raised to the 0.6 gives me 3.98 is the ratio of base to acid, which makes sense because if we go back and actually look at the graph, right, it tells us that the pH of the solution we're looking at is 4.7. Well, that is well beyond the half equivalence point, which tells me that I should have a higher concentration of base than I would of my acid, right? Because 4.7 would be here. And that pH is indicating that the concentration of the ascorbic acid is less than that of the base. Okay, so the base should be in a higher amount, and that is verified by this calculation down here below. So pretty straightforward. Okay, let's keep moving on. Dehydroascorbic acid can be produced by reacting ascorbic acid with triiodide ion as represented in the following equation. The student runs 3 trials of the reaction with different initial concentration of HASC and I3-, producing the following data. And so we're given 3 different trials here with different initial concentrations and different rates of formation. It says here for number 1 that the rate law for the reaction looks like appears to be first order for both of them. It says explain how the data in the table supports the conclusion that the reaction is first order with respect to HASC. So we're only doing one of these. So that's quite nice. Remember that when we do this, we need to find 2 reactions. One where HASC changes, but the other one does not. So we're going to be looking at experiments 1 and 3 here because I3 does not change, but HASC does. The concentration of HASC changes by a factor of 2. And when I look at the rate also changes by a factor of 2. If you can't visualize that by seeing these 2 numbers, take the bigger number and divide it by the smaller number. So 4.914 times 10 to the negative 4th divided by 2.5457 times 10 to the negative 4th. And when we divide these values, we get 2. And remember that reaction order is exponential based. So we always ask ourselves this question when we get to this 2 to what power is 2? And the answer is 1. So using that as your justification, that is indicative of a first order reaction. The next part asks us to go through and calculate the value for K for the reaction, include units with your answer. So we'll just pick the first reaction here. We're just going to plug in the values for trial 1 into the rate expression here and solve for the value for K. So 2.457 times 10 to the negative 4th equals K times 0.450 times 1.200. Sorry, ran out of room. And now all we do is we just algebraically solve for the value for K here. So let's take 2.457 times 10 to the negative 4th, divide that by 0.450, and divide that by 1.20. And our value for K is 4.55 times 10 to the negative 4th. I always stress, make sure you include your proper units, and anytime you calculate the rate constant, it is always 1 over the unit for seconds, and since it was molarity per second, it's 1 over second for this. Next question. The triiodide ion is significantly more soluble in water than elemental iodine is. Identify an intermolecular force between I3 and water that is not present between I2 and water that could explain the difference in solubility. So if we just kind of break each of these down, I2 is a nonpolar molecule, right? Something bonded to itself, so it only has London dispersion forces. I3-, however, is a little bit trickier to deal with. We don't talk a lot about, at least I don't talk a lot about expanded octets here, but this is actually another nonpolar molecule. It is linear. I know it looks a little strange with those 3 lone pairs surrounding that central atom, but it is a nonpolar molecule and would only exhibit London dispersion forces. However, this is an ion, and so as a result, the predominant intermolecular force that we're looking at here is actually the ion dipole force that exists between the I3 molecule and water because it will be attracted to the hydrogens that are in water. So finding a lot of questions about intermolecular forces and water solubility with this particular AP exam. We had one at the very beginning when we talked about magnesium and sodium and whatnot, but you see another one that pops up here. So quite interesting to take a look at. So that's it for question 2. So if you just came to see question 2, thank you so much, and we will see you very, very soon. All right, moving on to question number 3.